So now that we've addressed linear velocity, let's talk angular velocity. So what happens in angular velocity is we're essentially talking about how fast we rotate about a point. All right, so if I had a fixed point, we're measuring how fast I rotate through that. Of course, a counterclockwise rotation is a positive rotation, and a clockwise is a negative rotation. But in terms of speed, if we had to talk about what our rotation, positive or negatively, but we're basically talking about how fast we swirl around a point. Now, of course, how fast do we measure that swirl? Well, we have usually some central angle that's given, right? And then we have to be given the time that it happens. So your angular velocity, which we use as omega, right, is basically the central angle that I sweep out divided by the time that it took me to sweep out the angle. So there is your angular velocity. Notice that it's very similar to the linear velocity, but what's different is that rather than a distance that we've traveled, we're talking about how much did I rotate, basically. So how much rotation occurred, and how long did it take us to go through that rotation? Again, to get everything in order here, we're usually measured in radians. So make sure that if you're given something in degrees, convert it to radians so everything's in play in terms of angular velocity. So your theta is measured in radians, and your time could be in minutes or seconds or hours, whatever the case might be. So the unit for this is usually radians per second, all right, or radians per minute, or radians per hour, whatever the case might be. So how much of an angle in radians do I sweep out per unit time is essentially our angular velocity, all right? So very, very different than that. Up here where we had feet per second or miles per hour or whatever the case might be. In this case, our theta will always be measured in radians. And then keep in mind, radians is actually unitless, right? When I like right here 4, I didn't have to necessarily write that rad because it's understood, all right, that we have that because we effectively divided feet by feet. All right, so it's kind of a unitless idea, even though we know what's happening there. All right, and I'm kind of taking us back into 3-1. Alrighty, so now that we have a formula for angular velocity, let's put it to use. So find the angular velocity for a central angle that is created by rotating 2 pi over 3 in 4 seconds. So in this case, I'm given the central angle, right? So we rotated around a point 2 pi over 3 radians, and the time that it took was 4 seconds. So the angular velocity using our formula, right, theta over t, is basically 2 pi over 3 divided by 4, right? And of course now we got to clean that up. 4, let's write that as a fraction. When I take fractions and I divide them, I am effectively multiplying by reciprocal. We got a nice dividing out that goes on here, and it looks like we're left with pi over 6. All right, and so this would be in rads per, in this case, second. Okay, so for this particular situation, right, if we rotate 2 pi over 3, which is effectively, I think, 120 degrees. So if I have a 120 degree rotation, if it takes me 4 seconds to do that, then my rate of spin, if you would, my rotation, my angular velocity is pi over 6. So in the next example, they're asking us to find the angular velocity of an hour hand in a watch. All right, so if we take an hour hand, right, there's basically, it's usually the shorter one, and then the longer one is usually the second hand. So basically we have to figure out, right, what is theta and how much time does it take us to sweep out that theta. And since we're talking about an hour hand, right, one full rotation, as a matter of fact, it goes clockwise, matter of fact, right, one full rotation that we have, right, in 1 hour, it's going to rotate 2 pi radians. All right, so in 1 hour's time, right, or excuse me, in a in a 12-hour time. Excuse me. Getting my time values. So in a 12-hour time, right, that's how long it takes for the hour hand to totally rotate and come back to where it started, right? Because there's 12 hours in that clock. So we're going to rotate a full rotation. So my angle is 2 pi. It's going to take us 12 hours to do that rotation. So we're now ready to find our angular velocity. The angular velocity is the angle that I swept out divided by the time that it took me to get there. And in this case, after a cancellation, we also end up with pi over 6. This will be rads, but this is pi over 6 radians per hour, not pi over 6 radians per second. So this guy obviously is much faster because that's 30 degrees. We're basically going a 30-degree rotation every second, whereas opposed to this, we're going about we're going 30 degrees every hour. All right, so that, all right, should basically talk about both velocities separately, all right, and how to find them and what they mean and our formulas for them. And so we're now ready to actually relate these two ideas, which hopefully you can see is not too hard, because as we rotate through an angle, through some unit time, not only are we rotating around a point, but we're also causing some distance, some arc length along the edge. So if I can see that on the circle here, how I can relate these two ideas, then of course there's got to be a way to relate the linear velocity to the angular velocity. And sure enough, there is. But we'll investigate that in another video coming soon. Talk to you guys in a bit.